For example 7.4.1, we're looking at confidence intervals for proportions. Suppose that a market research firm is hired to estimate the percent of adults living in a large city who have cell phones. 500 randomly selected adult residents in the city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 421 responded yes, they own cell phones. Using a 95% confidence level, compute a confidence interval estimate for the true proportion of adult residents in the city who have cell phones. Let's take a look at some keywords. We want a confidence interval estimate for a proportion. So I know that I'm looking for some confidence interval dealing with P, our population proportion. For our random variable, X can represent the number of people who own cell phones. And since we have people who own cell phones or not, we have two outcomes, success or failure. X is binomial in nature. Specifically, X has the binomial distribution of 500, because that's our n, and our probability is 421 divided by 500. Keep in mind that this 421 out of 500 is our point estimate p hat that we'll use when we construct the confidence interval. The big idea here, though, is because we've identified that it's binomial, we're going to use the normal distribution to find our critical values. Now, we could use the formula for error bounds, and the book steps through how we would do that. Just know that when they talk about using the calculator, we use Google or Excel to calculate that. So in the step about inverse norm to find the z alpha over 2, we're just going to go to Excel or Google and use norm.inv to get that same value. For Excel and Google, we're going to use a template instead. And what a template is really just a pre-programmed situation where we just enter in values and it calculates it for us. If you grab this template from the links online, you can see size of population n, if known. This data in here is previous data. It's junk. We're going to erase it in just a minute. Sample proportion p, if known. Number of successes in sample, if known. So we'll have one of these three filled in, or possibly two. And then we need to know the sample size. We need to know the confidence level. And then down here in the white boxes, these are all formulas that will be calculated for us. And you can notice the formula switching as I move through up here. You can also see the explanation of what the formulas are doing over here in the blue. And this MOE that's here, this is what our book is calling the EBM, the error bound. So these are the error bound calculations. And then the upper and lower confidence limits are what our answer would be for our confidence interval. So let's fill out some of the information here based on our problem. And the problem that we have says there were 500 people surveyed. That's our sample size, 500. 421 responded yes. That's our number of successes. Using a 95% confidence interval, or a 95% confidence level, compute a confidence interval estimate. So we have that 95% confidence level there. And notice that everything is calculated out. Our sample proportion, p hat, is 0.842. That's going to be our point estimate for the population proportion. Our critical value is 1.96. That should look familiar for a 95% confidence interval using the normal distribution. Our standard error, this is the standard error for the mean. And then our margin of error calculation here. And then the margin of error is added and subtracted to p hat to get these upper and lower confidence limits. So 0.810 to 0.874 if we round to 3 decimal places. And I'm going to put that up over in the corner for a moment, 0.810 to 0.874. And that's just from using the template. If we're interpreting it, we would say we are 95% confident the true population proportion for cell phone owners in the large city is between, we could put it in percentages, 81% and 87.4%. Looking at this same problem, only doing it by hand instead, or at least mostly by hand, instead of using the table, instead of using the template, we could do this mostly by hand. So same problem, let's write down some information. We have X being the number of cell phone owners for the random variable. X is binomial still, with 500 and 421 over 500 being the parameters. Since it's binomial, we can use the standard normal distribution for our z alpha over 2's. N is 500, X is 421, so our p hat, the sample proportion, is 421 divided by 500, which is equal to 0.842 as a decimal number. Once we have p hat, we can also get q hat, 1 minus p hat, which would be 0.158. And I'm using hats, and the book uses the little apostrophes or primes. It's just different notation. They mean the same thing. So changing these hats into primes, they still mean sample proportions. For our confidence level, 0.95, that means alpha is going to be 1 minus the confidence level at 0.05. If alpha is 0.05, then alpha over 2 will be 0.025. And z alpha over 2, we would put in norm.s.inv 0.025. Norm.s.inv 0.025 will give us negative 1.9599, so 1.96. But remember that the standard normal is symmetric, so we're really just wanting the positive 1.96. We add and subtract the error bound for proportions in order to take care of that negative sign that we encounter, shrinking some of that content out of our way so we have some more room to work. We can now calculate our error bound for proportions, z alpha over 2 times square root p prime q prime over n, 1.96 square root p 0.842, q prime 0.158, and n is 500. And we'll put that into our calculator, 1.96 times, big parentheses, 0.842 times 0.158 divided by 500. Take the square root of all of that and hit enter, and we get 0.0319, which would round to 0.032. And now we need to add and subtract 0.032 to p hat. So we set up our interval, p hat, p prime, whichever one you want to do. Proportion is in the middle, p prime plus our error bound, EBP, p prime plus our EBP, and then p prime minus our EBP. And plugging in the numbers, 0.842 minus 0.032. 0.842 plus 0.032, and we'll end up with 0.810 less than p less than 0.874. And if I scroll back up here, that's exactly what we got from the template. And we should get the same answer. We're doing the same problem. So we could write this also as interval notation, and that would also lead us to the exact same big picture conclusion for the explanation. We are 95% confident the true population proportion for cell phone owners in the large city is between 81% and 87.4%. That means if we repeat over and over and over taking samples and creating confidence intervals, that 95% of our confidence intervals would contain the true value for the population proportion.